An explicit forward Euler method is used to numerically integrate the differential equation dy by dt is equal to y using a time step of 0.1. With the initial condition y at t is equal to 0 is 1, the value of y1 computed by the method is, so we need to find the value of y1 corrected to 2 decimal place. So the Euler's method to generate a numerical solution to an initial value problem is given by the form y dash is equal to f of t comma y, where y of t naught is equal to y naught. Okay. Also, the next term or the next step will be given by y of n plus 1 will be equal to yn plus h times of f of tn comma y. Now in the problem, the given differential equation is dy upon dt is equal to y. Okay, so let's write it here. The given differential equation is dy by dt is equal to y. This we can also write as y dash is equal to y. Now the initial value is given as t naught is equal to 0, and for t naught to be 0, y naught value is equal to 1, and the time step is given as h is equal to 0.1. These values are mentioned in the problem. Now let's use the Euler's method for numerical integration. As already established, next term y of n plus 1 is always given by y of n plus h times of f of tn comma yn. Okay, so we can also write it as yn plus h of yn. Okay, for this case it is yn because the differential equation given is dy by dt is equal to y. Okay, so let's write it as, if we take yn as common, this will be 1 plus h. Now let's calculate the first term. So y of 0.1 will be equal to y1, so this will be equal to y naught into 1 plus h. Okay, so y naught is 1 and 1 plus h is 0.1, so this y1 will become 1.1. So this will be the value of y1. Now let's calculate y2, that is y of 0.2. This will be equal to y2, that is y1 into 1 plus h. So y1 we have 1.1 into 1 plus 0.1. Okay, so this will be equal to 1.21. Now let's calculate y of 0.3. So this will be equal to y3, and this is y2 into 1 plus h. So y2 is 1.21 and this is 1. Or we can just directly write here 1.1. Okay, in all the problems, in all the iterations, we can just directly write 1.1. So this will be 1.331. Now y of 0.4 will be equal to y4. So y4 will be y3 times of 1.1. So y3 is 1.331 multiplied by 1.1. So this value will be 1.4641. Y of 0.5, that is y5 will be equal to y4 times 1.1, so 1.4641 into 1.1, this is 1.61051. Similarly, let's calculate y0.6. y6 is equal to 1.61051 times 1.1. This is 1.77156. Y of 0.7 is equal to y7 is equal to 1.77156 multiplied by 1.1, that is equal to 1.9487. Now y8 or y0.8, y of 8 will be equal to 1.9487 multiplied by 1.1, that is equal to 2.14588. Okay, now we are getting closer. We need to find y1 in step of 0.1, so this calculation may look very lengthy, but you will be having calculator for this calculation, so you need not to worry about this type of problems. And please don't think that the problem is lengthy, so you have to leave this problem. Okay, please do try to do these problems in the beginning itself. So this will be 2.357947, and now at the end we are having y of 1, that is equal to y10. So we had 10 steps to follow to calculate this value. 2.357947 multiplied by 1.1, and so we will get y1. So let's write here first 2.59374. so this will be equal to 2.59, correct to 2 decimal places. Okay, let's go back to the problem. So the value of y1 computed in 10 steps will be equal to 2.59. To study more on explicit forward Euler method for numerical integration, you can refer to the NPTEL course lecture number 14, solution of differential equation on Taylor series and Euler's method, by Professor Saurav Basu of the Department of Physics at IIT Guwahati.